Kris, who will speak on lunar prospecting and mining. And I'm going to give him a short introduction. You can read his extensive accomplishments in your program. He's the Vice President and Director of Exploration Technology Group at Honeybee Robotics. And his expertise includes terrestrial and extraterrestrial robotic drilling, excavation, sample handling and processing, geotechnical systems and sensors. He's been part of many NASA programs, including the Mars program, also part of the Resource Prospector program right now. So, do we have Kris online?
Yeah. Can you hear me?
Yeah. Hello, Kris. How are you doing? This is Laurent.
How are you doing? My apologies, I couldn't make it. I was actually attending the very first offer mining forum a couple of years ago. I couldn't make the second one and this one, but I promise I'll come next time.
That sounds good.
I'll book it way in advance. I know you guys short of time, so I'm gonna try to maybe rush through some of the slides, but I'm really excited that I can talk to you at least remotely. The topic concerns lunar prospecting and mining, and there is a reason why you need to do prospecting and mining. So first, the ISRU, or in situ resource utilization as such, is a two-step process, not just one, it's a two-step. The very first one is exploration. Within exploration, in the case of ISRU, the goal is to determine water reserves. So what are those reserves? Those reserves are material in situ, proven to be feasible to extract and process with proposed mining approach and techniques. It's very important to understand that it has to be feasible to extract. Just because it's there doesn't mean it's a proven water resource or reserves. So exploration needs to answer three questions: how much, where, and how to extract. So there has to be a business case as well. Once you nail down the exploration part, then you can go into production and processing. And during the second step, you essentially follow the process you have outlined in the exploration, how to extract it, but how to extract it in a sort of larger commercial sense. So you next a very important step about actually information about the South Polacan Basin on the Moon. It's not just about water. When we go away, it's not just about water. As Kris pointed out, there is a bunch of other compounds at different concentrations. For some people, these compounds, it's an unnecessary evil. You have to take it out before you can get clean water. For other folks, this could be another resource. So it depends which side of the camp you are, whether it's a resource or not. You will have to deal with this. Many of you within the audience have a mining background, and as you know, it's not just about ore. We worry about these parts per billion or parts per million contaminants that are extremely difficult to remove, which make ore very expensive to process or even unfeasible to process. That's why we have to be very careful what we call the resource and how to extract it. So again, it's not just water. It's also not just about water. To get down to the craters, there are a couple of other things we need to worry about. The first one is how many days of sunlight do we get? Where are the hot spots? Where is the highest concentration of water? How deep water actually can be found within the first meter of the surface? And is it easy to get down the slope, or is it just too steep? As we know, Curiosity rover can only drive out maybe 20-25 degree slope. So if there is a significant resource, 35-40 degree down slope, we might not be able to get. So it's not just about water. Going back to the first step, which is exploration. NASA is putting together the next mission, which is called the Resource Prospector. This rover is around twice as big as a Mars exploration rover and probably half the size of a Curiosity rover. It has been designed to drive around the moon and prospect for volatiles. To do so, it has a couple of instruments. Right in front, there is a neutron spectrometer that's looking for hydrogen hotspots. And hydrogen is an indication of water reserves. Once you find these hotspots, then the drill it goes down to up to a meter depth, and as it penetrates below the surface, it removes the cuttings. These cuttings are being watched in real time by near-infrared spectrometer, which looks for not only volatile content, but also mineral content. If we find something of interest, the drill captures the sample and delivers to the GCMS, gas chromatograph mass spectrometer, which does much better job of analyzing volatiles, not only water, but also other the parts per million, parts per billion type of volatiles. So our company has been focusing on drilling. So the past decade, we have developed a couple of different drilling approaches, ranging from sonic, so it's pretty big. It's sort of like a vibrating system, sort of like a toothbrush, but it's much bigger. Then ultrasonic, percussive, and rotary. We've done a bunch of tests under different conditions and determined that percussive and rotary systems are actually the best. Percussive is really good for extremely hard formations, whereas rotary is sufficient for relatively weak formations. So our next generation drill was rotary percussive with these two modes of drilling completely decoupled. So you could kick in percussion only when you need it. And over the past couple of years, we went up the technology readiness level from 4 to 5, and finally we reached 6 beginning of this year. The sampling approach follows the bite sampling, which means the bottom flutes are designed to capture the sample. That's our bite. And top flutes are designed to remove the sample in an efficient manner. So we drill down in 10 centimeter bites, we capture the sample, we pull out, and as we're pulling out, we're rotating the auger. The auger is in contact with the brush, brushes of the sample straight into the cup. And then we go back into the same hole, capture another 10 centimeters, pull out, and brush it off into the cup for analysis. So in this particular approach, stratigraphy is preserved in approximately 10 centimeter bites all the way down to 1 meter depth. Because the auger sits on the surface while the material is being analyzed, it gives time for subsurface to cool down if by chance you heat it up during the drilling process. Because you also not convey material all the way to the surface, but capture it in these 10 centimeter bites, you are much better in analyzing the material strength in situ, the power required to auger out to the surface, to auger material out to the surface is relatively low during this bite sampling concept, and as such, the power required to drill is predominantly much higher, and as a result gives you a much better indication of the material strength. And I call this approach also a low-risk approach. If something happens and for some reason you cannot penetrate below 60 centimeter depth, at least you've got 5 samples between the surface and 50 centimeters. This is how this bite sampling approach is implemented. You have a stratigraphy where top is relatively dry, and underneath you have ice-bearing material. You drill down in 10 centimeter bites until you get down to icy soil, you pull it out, and then as you pull out, you rotate, and the brush adjacent to the auger removes the sample, and the sample drops into the cup for analysis. So this actually approach works really well. To test it out, to test out the drilling and sample delivery, we've done a couple of test expeditions. One of them was to Antarctica, to dry valleys. We would end up with flying on B-212s. It would be dropped off for like two-week period in these regions of Antarctica that hasn't seen liquid water for a extended duration of maybe hundreds of years. As such, the water or ice that you see on the surface, it's all vapor deposited ice, sort of like on the moon. What you see on the surface here is a desert pavement. That's relatively dry material. You have to dig approximately a couple of inches below to get into ice-cemented ground. So from an analog standpoint, it's pretty accurate to what we would expect on the moon. So the surface is relatively dry, and the subsurface has ice-cemented soil. We've done a couple of drill deployments. A couple of them in ice-cemented ground, a couple of them in pure ice. Bottom line is we demonstrated you can drill a couple of meters below the surface with a penetration rate of around 1 meter an hour, approximate mechanical power of 100 watts, and a force on bed of around less than 100 newtons. And the last one, the force on bed of 100 newtons, is extremely important. It's very important to keep it as low as possible because of the low gravity on the surface of the moon. Obviously, we had to do tests under lunar condition. To do this, we flew over to NASA Glenn, which has a large lunar chambers. What you see here is our prototype drill mounted within a chamber. And on the left-hand side, you see the part of the drill dedicated to dispense the sample into 6 of the crucibles or cups that you see on the right-hand side. We used analog soil, which was doped with water up to 5%. It was compacted and frozen down to like minus 140 centigrade. The shroud around the chamber was keeping everything inside the chamber at around minus 100 centigrade. So this is how you assemble everything. It's quite a process. It takes a couple of days to assemble it and get everything set up before you can run a test. Here what you see is the bottom part of the chamber with the soil sample being lowered inside. This drill with this XY stage goes up on top. Then we put in the liquid nitrogen shroud, and on top we put in the vacuum lid. All of this takes a couple of days, and then cooling down takes another couple of days. So turnaround time for a test, which is essentially a couple of drilling cycles, is approximately a week. And these are some of the results. On the right-hand side, on the y-axis, it's a theoretical sublimation rate in gram per second, which is a function of the ambient temperature. So obviously, the higher the temperature, higher the sublimation rate. That's all in vacuum. On the y-axis, on the left-hand side, we have percent of water lost during sample capture and delivery. And these are the data points. So these data points line up pretty much perfectly along this theoretical sublimation curve. What it tells us is that to preserve a sample, we have to keep it cold. The moment we expose it to higher temperature, we run the risk of losing volatiles that we're supposed to analyze. We've done also remote operations between our location in Pasadena and a location at Johnson Space Center in Houston. This was to mimic operations on the moon, and this was successful. What you see here is a rover at NASA Johnson Space Center, drilling into different simulants and capturing the sun. So once we go to the moon, we capture the volatiles. We know how much, how deep. We determine there is a business case. So what's next? Next is a production. There are two issues when it comes to production. First one is excavation of icy soil. This graph shows compressive strength of a JSC1A lunar simulant doped with various water concentration at 77 Kelvin. These blue dotted lines marks where the strength of a commercial pump. You can quickly see that the lunar simulant, when it's saturated with water at cryogenic temperatures, is much harder, 2 to 3 times harder than concrete. This makes it very challenging to excavate it on the moon. On Earth, the way we do this, we drill, we use rotopercussive drills to make deep holes, and then we put explosives, and we blast everything away. On the moon, it's going to be tougher to do this. We tried other options. This option included a sort of jackhammering scoop. The scoop was the size of a strawberry scoop, just for scaling purposes. This rotopercussive hammer was delivering something like 4.5 joules per bar, which is quite significant. Unfortunately, we could not penetrate these icy simulants at only -20 centigrade, even with 3,000 newtons force and at 4.5 joules per bar. It was just too hard. The same simulant, actually, we managed to penetrate using rotopercussive drill. We realized it's going to be tough to dig it out, but it's going to be easy to drill it out. The second issue is
Kris, can you hear me?
Yeah.
Yeah, you have about 2 more minutes.
Okay, sounds good. The second issue is volatiles capture. And again, as alluded previously, if you don't, this graph essentially shows how much 1 micron of ice loses its mass as a function of different temperatures. And if you warm it up to 170 Kelvin, which is minus 170 C, it's going to be gone in a matter of minutes. So how to, given these two problems, volatile and losses and the excavation of a compacted soil, how would you do this? We looked at the 3 different water capture approaches. The first one is a sniffer. So you drill down, you heat it up, and you're hoping that volatiles will go past these holes and up the sniffer into the water capture area. The next one is an auger. You capture icy soil on the flutes, you pull back into the reactor, heat it up, and you sort of evolve the volatiles, and volatiles go and being captured into a sort of a cold finger. And the third one is coring auger. You go down, you stop, you heat up this ice core right in the center of the auger. Volatiles climb up, go through the perforated walls, and go to the ice finger, the cold finger. We've done a bunch of experiments in a vacuum chamber. Sniffer didn't work very well. Most of the ice was lost to the outside. The auger worked pretty well. We managed to get quite a bit of water. However, the coring system worked the best. We got most water during the extraction process. If you look at the energy efficiency, again, the corer was the best, followed by auger, followed by sniffer. Water recovery was also the highest for the corer, followed by auger, followed by sniffer. From a drilling standpoint, corer is also much more efficient than auger or a sniffer design, these two require full-face cut. As such, we have to cut this entire surface area of a material, whereas Core cuts only this very thin curve, and as such, it's much more efficient. And currently, we built the coring system. We're doing all the tests in a vacuum chamber, in a thermal vacuum chamber, and analyzing the data. Data is looking very good so far. And these are the potential architectures. The first one is obviously on the rover. We're using the heat from the MMRTGs to warm up the ice, and we can have 1 or 2 or 3 of those. Another one for asteroids, these reactors can be placed on the legs of a asteroid extraction system called Spider, and we drill at the oblique angles to sort of anchor ourselves to the asteroid. So to conclude, ISRU is 2 aspects. First one is exploration, and the second one is production. 2 other things, it's not just water on the moon, and it's not just about water. Water-rich soil at cryogenic temperatures is like salt. Ice sublimes very quickly in vacuum at temperatures above 110 Kelvin. Exploration can be accomplished with Lunar Resource Prospector. Production can be done with planetary volatiles extraction or Spider system. And I'd like to acknowledge a couple of folks who made all this research possible. Rob Mueller and Jackie Quinn from NASA Kennedy, Aaron Pass and Jim Smith from Kennedy, and Jerry Sanders from NASA Johnson. As well, I'd like to acknowledge also a couple of programs, NASA SDIR, HUMD, Advanced Exploration Systems, and various NASA Science and Mission Directorate funding PEDEC, ASTRO, and NASA. Thank you very much.
All right, Kris, thank you very much for the presentation. I'm going to allow one question because you have covered a lot, but we're on time constraint because we have a dinner in town planned on a cruise. So one question, please. Anybody? Okay, Kris, I think thank you very much again, and
Sure.
we look forward to you being in person on the next one.
Sounds good. Thank you so much. Enjoy the rest of the conference, guys. Bye-bye.
Okay, we're going to move on to the next speaker, and